Sections 9 through 13 of On the Elementary Electrical Charge and the Avogadro Constant. Physical Review, Volume 2, Number 2. By Robert Andrews Millikan. This is a LibriVox recording. All LibriVox recordings are in the public domain. For more information or to volunteer, please visit LibriVox.org. Section 9. The Observations. The record of a typical set of readings on a given drop is shown in Table 4. The first column, headed T sub G, gives the successive readings on the time of descent under gravity. The fourth column, headed T sub capital F sub C, gives the successive times of ascent under the influence of the field capital F as measured on the hip chronoscope. These two columns contain all the data which is used in the computations. But in order to have a test of the stagnancy of the air, a number of readings were also made with a stopwatch on the times of ascent through the first half and through the whole distance of ascent. These readings are found in the second and third columns, the times for the first half under the head 1/2 T sub capital F sub G, the times for the whole distance under the head T sub capital F sub G. It will be seen from these readings that there is no indication whatever of convection, since the readings for the 1/2 distance have uniformly 1/2 the value of the readings for the whole distance, within the limits of error of a stopwatch measurement. This sort of a test was made on the majority of the drops, but since no further use is made of these stopwatch readings, they will not be given in succeeding tables. The fifth column, headed 1/T sub capital F, contains the reciprocals of the values in the fourth column after the correction found from tables 2 and 3 has been applied. The sixth column contains the successive differences in the values of 1/T sub F resulting from the capture of ions. The seventh column, headed N', contains the number of elementary units caught at each change, a number determined simply by observing what number the quantity just before it in column 6 must be divided to obtain the constancy shown in the eighth column, which contains the successive determinations of open parenthesis 1/T sub capital F prime minus 1/T sub capital F, close parenthesis, sub 0. See section 6. Similarly, the ninth column, headed N, gives the total number of units of charge on the drop, a number determined precisely as in the case of the numbers in the seventh column, by observing by what numbers the successive values of 1/T sub G plus 1/T sub capital F must be divided to obtain the constancy shown in the 10th column, which contains the successive values of open parenthesis 1/T sub G plus 1/T sub capital F, close parenthesis, sub 0. Since N' is always a small number, and in some of the changes almost always has the value 1 or 2, its determination for any change is obviously never a matter of the slightest uncertainty. On the other hand, N is often a large number, but with the aid of the known values of N', it can always be found with absolute certainty, so long as it does not exceed, say, 100 or 150. It will be seen from the means at the bottom of the 8th and the 10th columns that in the case of this drop, the two ways discussed in section 6 of obtaining the number, which when multiplied by mg T sub G over capital F is the elementary electrical charge, yield absolutely identical results. In order to show the sort of consistency attained in this work, the complete records are given in tables 5, 6, 7, 8, and 9 of 5 drops of practically the same size taken at very nearly the same pressures. These are the only drops of this size which were observed with the present arrangement, so that they represent the regular run of observations rather than the selected group. The symbols in the last column, capital V sub I, capital V sub F, T, P, V sub 1, and A, stand for initial volts, final volts, temperature, pressure, velocity under gravity, and radius, respectively. It will be seen from the second columns, see Table 5, that in general, in spite of the precautions taken against evaporation, 1c, page 388, the drops do evaporate very slowly, since with a given charge, the speed in the field very slowly increases. It is for this reason that the numbers in the next to last column tend to increase very slightly. This slow change introduces no error into E sub 1, provided corresponding values of T sub G, T sub capital F, and capital V, volts, are combined to obtain E sub 1. The mean values taken throughout the same time interval constitute such corresponding values. On account of this slow change, however, the readings from which the differences 1 over T sub capital F prime minus 1 over T sub capital F are taken should be separated by as small a time interval as possible. It is for this reason that in Table 5, for example, to obtain the difference 1 over T sub capital F prime minus 1 over T sub capital F, corresponding to the change from T sub capital F equals 45 seconds to T sub capital F equals 694 seconds, the last two of the 45-second readings are averaged instead of the whole four. It is worthy to note, too, in this connection, that if a change in the time in the field takes place first from 45 seconds to 694 seconds, and then immediately back again to the 45-second value, the mean of the two values of 1 over T sub capital F prime minus 1 over T sub capital F thus obtained is independent of any error arising from the evaporation of the drop. For this reason, the mean value of the quantity fraction 1 over n prime, n fraction, times open parenthesis 1 over T sub capital F prime minus 1 over T sub capital F is in general much more trustworthy than might be inferred from the variation in the individual numbers from which this mean is obtained. Nevertheless, in practically all of the following work, in view of the large number of observations in the T sub G column, the mean at the bottom of the column 1 over n times open parenthesis 1 over T sub G plus 1 over T sub capital F, close parenthesis, is considered more trustworthy than the mean at the bottom of the column 1 over n prime times open parenthesis 1 over T sub capital F prime minus 1 over T sub capital F, close parenthesis, and it has been, in fact, exclusively used in the computation of E sub 1. Only in the case of 2 or 3 of the fastest drops, tables 16 and 17, are the uncertainty in open parenthesis 1 over T sub G plus 1 over T sub capital F, close parenthesis, sub 0, greater perhaps than those in open parenthesis 1 over T sub capital F prime minus 1 over T sub capital F, close parenthesis, sub 0. And in these cases the two were so near together that there was no object in using the latter instead of the former. It should be stated that all time intervals longer than 150 seconds were measured with the stopwatch rather than with the chronoscope, and are not subjected to the corrections in tables 2 and 3. In general, too, only differences in T sub capital F prime minus T sub capital F amounting to as much as 20 seconds are used in the determination of 1 over T sub capital F prime minus 1 over T sub capital F, since obviously the observational error is large when T sub capital F prime minus t sub capital F is small. A study of tables 4 to 9 shows first a striking agreement between the values of open parenthesis 1 over t sub capital F prime minus 1 over t sub capital F close parenthesis sub 0 and open parenthesis 1 over t sub g plus 1 over t sub capital F close parenthesis sub 0. The largest divergence being found in Table 5, where it amounts to 0.3%. And second, a satisfactory agreement between the values of E sub 1 obtained from the different drops of approximately the same size, the largest divergence of mean value being here too, 0.3%. A few typical records of observations made at different pressures, see P, last column, and on drops of different sizes, see A, last column, are presented in tables 10 to 19. Table 20 contains a complete summary of the results obtained on all of the 58 different drops upon which complete series of observations like the above were made during a period of 60 consecutive days. It will be seen from this table that these observations represent a 30-fold variation in L over A, from 0.016, drop number 1, to 0.444, drop number 58, a 17-fold variation in P, from 4.46 centimeters, drop number 56, to 76.27 centimeters, drop number 10, a 12-fold variation in A, from 4.69 times 10 to the negative 5th power centimeters, drop number 28, to 58.56 times 10 to the negative 5th centimeters, drop number 1, and a variation in the number of free electrons carried by the drop, from 1 on drop number 28 to 136 on drop number 56. The time of fall of drop number 28 was also tested when it was completely discharged, as have been the times of many other drops which carried most of the time but one electron. Much larger variations, both in A and P, and therefore in L over A, might have been used, and have in fact been used, for finding the law of fall of a drop through rarefied air. But for the end here sought, namely the most accurate possible determination of E, it was found desirable to keep the T sub g interval for the most part between the limits 10 seconds and 40 seconds, in order to avoid chronograph errors on the one hand, and Brownian movement irregularities on the other. That neither of these sources of error is appreciable in these observations may be seen from a study of tables 4 through 19, which are thoroughly representative of the work on all the drops. Section 10. Results and Discussion. It will be seen at once from equation 4 that the value of E is simply the value of E sub 1 for which L over A equals 0. So that if successive values of E sub 1 to the 2/3 power are plotted as abscissae, and of L over A as ordinates, the intercept of the resulting curve on the E sub 1 to the 2/3 power axis is E to the 2/3 power. Furthermore, if capital A is a constant, then the curve in question is a straight line, and A is the slope of this line divided by the y-intercept. See equation 9. In view of the uncertainty in L due to the fact that K in the equation, eta equals KNM C bar L, has never been exactly evaluated, it was thought preferable to write the correction term to Stokes' law, C 2 and 3, in the form open parenthesis 1 plus B over PA, close parenthesis, to the negative 1 power, instead of in the form open parenthesis 1 plus capital A L over A, close parenthesis, to the negative 1 power. and then to plot e sub 1 to the 2/3 against 1 over PA. Nevertheless, in view of the greater ease of visualization of L over A, all the values of this quantity corresponding to successive values of 1 over PA are given in Table 20, K being taken, merely for the purposes of this computation, as 0.3502 Boltzmann. Figure 2 shows the graph obtained by plotting the values of e sub 1 to the 2/3 against 1 over PA for the first 51 drops of Table 20. And Figure 3 shows the extension of this graph to twice as large values of 1 over PA and e sub 1 to the 2/3 power. It will be seen that there is not the slightest indication of a departure from a linear relation between e sub 1 to the 2/3 power and 1 over PA up to the value 1 over PA equals 620.2, which corresponds to a value of L over A of 0.4439. See drop number 58, Table 20. Furthermore, the scale used in the plotting is such that a point which is one division above or below the line in Figure 2 represents in the mean an error of 2 in 700. It will be seen from Figures 2 and 3 that there is but one drop in the 58 whose departure from the line amounts to as much as 0.5%. It is to be remarked, too, that this is not a selected group of drops, but represents all of the drops experimented upon during 60 consecutive days, during which time the apparatus was taken down several times and set up anew. It is certain, then, that an equation of the form 2 holds very accurately up to L over A equals 0.4. The last drop in Figure 3 seems to indicate the beginning of a departure from this linear relationship. Since such departure has no bearing upon the evaluation of E, discussion of it will be postponed to another paper. Attention may also be called to the completeness of the answers furnished by Figures 2 and 3 to the questions raised in Section 6. Thus, drops number 27 and 28 have practically identical values of 1 over PA, but while number 28 carries during part of the time but 1 unit of charge, see Table 20, drop number 27 carries 29 times as much, and it has about 7 times as large a diameter. Now, if the small drop were denser than the large one, see Assumption 3, Section 6, or if the drag of the median upon the heavily charged drop were greater than its drag upon the one lightly charged, see Assumption 1, Section 6, then for both these reasons, drop 27 would move more slowly relative to drop 28 than would otherwise be the case. And hence e sub 1 to the 2/3 power for 27 would fall below e sub 1 to the 2/3 power for drop 28. Instead of this, the two e sub 1 to the 23rd powers fall so nearly together that it is impossible to represent them on the present scale by two separate dots. Drops 52 and 56 furnish an even more striking confirmation of the same conclusion, for both drops have about the same value for L over A, and both are exactly on the line, though number 56 carries at one time 68 times as heavy a charge as number 52, and has 3 times as large a radius. In general, the fact that Figures 2 and 3 show no tendency whatever on the part of either the very small or the very large drops to fall above or below the line is experimental proof of the joint correctness of assumptions 1, 3, and 2b of Section 6. The correctness of 2a was shown by the agreement throughout tables 4 to 19 between 1 over n prime times open parenthesis 1 over t sub capital F prime minus 1 over t sub capital F close parenthesis and 1 over n times open parenthesis 1 over T sub G plus 1 over T sub capital F, close parenthesis. The values of e to the 2/3 power and b, obtained graphically from the y-intercept and the slope in figure 2, are e to the 2/3 power equals 61.13 times 10 to the negative 8th power, and b equals 0.0006254. P being measured, for the purposes of figure 2 and of this computation, in millimeters of mercury at 23 degrees centigrade, and A being measured in centimeters. The value of capital A, equations 2 and 3, corresponding to this value of capital B, is 0.874 instead of 0.817 as originally found. Cunningham's theory gives, in terms of the constants here used, capital A equals 788. Instead, however, of taking the result of this graphical evaluation of e to the 2/3 power, it is more accurate to reduce each of the observations on e sub 1 to the 2/3 power to e to the 2/3 power by means of the above value of capital B and the equation 14, e to the 2/3 power times, open parenthesis, 1 plus b over pa, close parenthesis, equals e sub 1 to the 2/3 power. The results of this reduction are contained in the last column of Table 20. These results illustrate very clearly the sort of consistency obtained in these observations. The largest departure from the mean value found anywhere in the table amounts to 0.5%, and the probable error of the final mean value computed in the usual way is 16 in 61,000. Instead, however, of using this final mean value as the most reliable evaluation of e to the 2/3 power, it was thought preferable to make a considerable number of observations at atmospheric pressure on drops small enough to make T sub g determinable with great accuracy, and yet large enough so that the whole correction term to Stokes' law amounted to but a few percent, since in this case, even though there might be a considerable error in the correction term constant b, such error would influence the final value of e by an inappreciable amount. The first 23 drops of Table 20 represent such observations. It will be seen that they show slightly greater consistency than do the remaining drops in the table, and that the correction term reductions for these drops all lie between 1.3%, drop number 1, and 5.6%, drop number 23. So that even though B were in error by as much as 3%, its error is actually not more than 0.5%, e to the 2/3 power would be influenced by that fact to the extent of but 0.1%. The mean value of e to the 2/3 power obtained from the first 23 drops is 61.12 times 10 to the negative 8th power, a number which differs by 1 part in 3,400 from the mean obtained from all the drops. When correction is made for the fact that the numbers in Table 20 were obtained on the basis of the assumption eta sub 23 equals 0.0001825, instead of eta sub 23 equals 0.0001824, see Section 2, the final mean value of e to the 2/3 power obtained from the first 23 drops is 61.085 times 10 to the negative 8th power. This corresponds to e equals 4.774 times 10 to the negative 10th power electrostatic units. Since the value of the Faraday constant has now been fixed virtually by international agreement at 9,650 absolute electromagnetic units, and since this is the number capital N of molecules in a gram molecule times the elementary electrical charge, we have capital N times 4.774 times 10 to the negative 10th power equals 9,650 times 2.9990 times 10 to the 10th power. Therefore, capital N equals 6.062 times 10 to the 23rd power. Although the probable error in this number computed by the method of least squares from Table 20 is but 1 part in 3,000, it would be erroneous to infer that E and capital N are now known with that degree of precision, for there are 4 constant factors entering into all of the results in Table 20 and introducing uncertainties as follows. The coefficient of viscosity, eta, which appears in the 3/2 power, introduces into E and capital N a maximum possible uncertainty of 0.1%. The distance between the condenser plates, 16.00 millimeters, is correct to 0.01 millimeters, and therefore, since it appears in the first power in E, introduces a maximum possible error of something less than 0.1%. The voltmeter readings have a maximum possible error of rather less than 0.1% and carry this in the first power into E and capital N. The crosshair distance, which is uniformly duplicatable to 1 part in 1,000, appears in the 3/2 power and introduces an uncertainty of no more than 0.1%. The other factors introduce errors which are negligible in comparison. The uncertainty in E and capital N is then that due to 4 continuous factors, each of which introduces a maximum possible uncertainty of 0.1%. Following the usual procedure, we may estimate the uncertainty in E and capital N as the square root of the sum of the squares of these 4 uncertainties, that is, as 2 parts in 1,000. We have then finally E equals 4.774 plus or minus 0.009 times 10 to the negative 10th power, and capital N equals 6.062 plus or minus 0.012 times 10 to the 23rd power. The difference between these numbers and those originally found by the oil drop method, viz. E equals 4.891 and capital N equals 5.992, is due to the fact that this much more elaborate and prolonged study has had the effect of changing every one of the 3 factors eta, capital A, and D, crosshair distance, in such a way as to lower E and to raise capital N. The chief change, however, has been due to the elimination of the faults of the original optical system. Section 11. Comparison with other measurements. So far as I am aware, there is at present no determination of E or capital N by any other method which does not involve an uncertainty at least 15 times as great as that represented in the above measurements. Thus, the radioactive method yields in the hands of Reginer a count of the alpha particles which gives E with an uncertainty which he estimates at 3%. This is as high a precision, I think, as has yet been claimed for any alpha particle count, though Geiger and Rutherford's photographic registration method will doubtless be able to improve it. The Brownian movement method yields results which fluctuate between Perrin's value, E equals 4.24 times 10 to the negative 10th power, and Fletcher's value, 5.01 times 10 to the negative 10th power, with Svedberg's measurements yielding the intermediate number, 4.7 times 10 to the negative 10th power. The radiation method of Planck yields capital N as a product of C sub 2 to the 3rd power and sigma. The latest Reichseinstadt value of C sub 2 is 1.436 to the 8th power, while Koblenz, as the result of extraordinarily careful and prolonged measurements, obtains 1.4456. The difference in these two values of C sub 2 to the 3rd power is 2%. Westphal estimates his error in the measurement of sigma at 0.5%, though reliable observers differ in it by 5% or 6%. We may take then 3% as the limit of accuracy thus far attained in measurements of E or capital N by other methods. The mean results by each one of the 3 other methods fall well within this limit of the value found above by the oil drop method. Section 12. Computation of other fundamental constants. For the sake of comparison and reference, the following fundamental constants are recomputed on the basis of the above measurements. 1. The number n of molecules in 1 cc of an ideal gas at 0 degrees 76 is given by n equals capital N over capital V, which equals 6.062 times 10 to the 23rd over 22,412, which equals 2.705 times 10 to the 19th power. 2. The mean kinetic energy of agitation, capital E sub 0, of a molecule at 0 degrees centigrade is given by P capital V equals 1/3 capital N M U squared, which equals 2/3 capital N capital E 0, which equals capital R capital T. Therefore, capital E 0 equals 3/2 P sub 0 V sub 0 over capital N, which equals fraction numerator 3 times 1,013,700 times 22,412, denominator 2 times 6.062 times 10 to the 23rd, and fraction, which equals 5.621 times 10 to the negative 14th power ergs. 3. The constant epsilon of molecular energy defined by capital E sub 0 equals epsilon capital T is given by epsilon equals capital E sub 0 over capital T, which equals 5.621 times 10 to the negative 14th power over 273.11, which equals 2.058 times 10 to the negative 16th power ergs over degrees. 4. The Boltzmann entropy constant K, defined by capital S equals K log capital W, is given by K equals capital R over capital N, which equals P sub 0 capital V sub 0 over capital T capital N, which equals 2/3 epsilon, which equals 1.372 times 10 to the negative 16th power ergs over degrees. All of these constants are known with precisely the accuracy attained in the measurement of E. 5. The Planck Wirkungsquantum H can probably be obtained considerably more accurately as follows than in any other way. From equation 292, page 166 of the Wärmestrahlung, we obtain H equals K to the 4/3 power over C times open parenthesis 48 pi alpha over A close parenthesis to the 1/3 power, which equals fraction numerator open parenthesis 1.372 times 10 to the negative 16th power close parenthesis to the 4/3 power. Denominator 2.999 times 10 to the 10th power. End fraction. Times, open parenthesis, fraction. Numerator 48 pi times 1.0823. Denominator 7.39 times 10 to the negative 15th power. End fraction, close parenthesis, to the 1/3 power, which equals 6.620 times 10 to the negative 27th power, which gives h with the same accuracy attainable in the measurement of k to the 4/3 power over a, in which a is the Stefan-Boltzmann constant. If Westphal's estimate of his error in the measurement of this constant is correct, viz. 0.5%, it would introduce an uncertainty of but 0.2% into h. This is about that introduced by the above determination of k to the 4/3. Hence, the above value of h should not be in error by more than 0.4%. 6. The constant c sub 2 of the Wien-Planck radiation law may also be computed with much precision from the above measurements. For, also from equation 292 of the Wärmestrahlung, we obtain c sub 2 equals, open parenthesis, 48 pi alpha k over a, close parenthesis, to the 1/3 power, which equals, open parenthesis, fraction, numerator, 48 pi times 1.0823 times 1.372 times 10 to the negative 16th power, denominator, 7.39 times 10 to the negative 15th power, end fraction, close parenthesis, to the 1/3 power, which equals 1.4470 centimeter degrees. Since both k and a here appear in the 1/3 power, the error in c should be no more than 0.2%, provided Westphal's error is no more than 0.5%. The difference between this and Koblenz's mean value, viz. 1.4456, is but 0.1%. The agreement is then entirely satisfactory. A further independent check is found in the fact that Day and Sossman's location of the melting point of platinum at 1755 degrees centigrade is equivalent to a value of c sub 2 equals 1.4475. On the other hand, the last Reichenstalt value of c sub 2, viz. 1.437, is too low to fit well with these and Westphal's measurements. It fits perfectly, however, with a combination of the above value of E and Shakespeare's value of sigma, viz. sigma equals 5.67 times 10 to the negative 5th power. Section 13. Summary. The results of this work may be summarized in the following table, in which the numbers in the error column represent the case of the first 6 numbers, estimated limits of uncertainty, rather than the so-called probable errors, which would be much smaller. The last 2 constants, however, involve Westphal's measurements and estimates and Planck's equations, as well as my own observations. Table 21. Elementary electrical charge. E equals 4.774 plus or minus 0.009 times 10 to the negative 10th power. Number of molecules per gram molecule. Capital N equals 6.062 plus or minus 0.012 times 10 to the 23rd power. Number of gas molecules per cc at 0 degrees 76. n equals 2.705 plus or minus 0.005 times 10 to the 19th power. Kinetic energy of a molecule at 0 degrees centigrade, capital E sub 0 equals 5.621 plus or minus 0.010 times 10 to the negative 4th power. Constant of molecular energy, epsilon equals 2.058 plus or minus 0.004 times 10 to the negative 16th power. Constant of the entropy equation, K equals 1.372 plus or minus 0.002 times 10 to the negative 16th power. Elementary Wirkungsquantum, H equals 6.620 plus or minus 0.025 times 10 to the negative 27th power. Constant of the Wien displacement law, C sub 2 equals 1.4470 plus or minus 0030. I take pleasure in acknowledging the able assistance of Mr. J. Yinbong Li in making some of the above observations. Mr. Li has also repeated with my apparatus the observations on oil at atmospheric pressure, with results which are nearly as consistent as the above. Using my value of B, he obtains as a mean of measurements on 14 drops a value of E which differs from the above by less than 1 part in 6,000, although its probable error, computed as in the case of Table 20, is 1 part in 2,000. Ryerson Physical Laboratory, University of Chicago, June 2, 1913. End of sections 9 through 13. End of On the Elementary Electrical Charge and the Avogadro Constant. Physical Review, Volume 2, Number 2, by Robert Andrews Millikan.